Hello, so let me begin this topic with this concept called electronegativity. Now, electronegativity describes the tendency of an atom or the functional group to attract electrons or electron density to itself. It means that how easy for this element to attract electrons to itself. Now, we have a scale for electronegativity for all the elements in the whole periodic table, and these are some of the numbers that you should know. You don't have to know the exact value, but you should know the relative values, which one is higher, which one is lower. We know for sure that fluorine is the boss. In the whole periodic table, fluorine is the most reactive non-metal. It likes to grab any electrons around. Basically, it's like electronegativity means, right, you arrange a single atom of all the elements in the whole periodic table in a whole campfire in a circular form, and I throw in one electron right in the middle of the campfire, and who will get 6 electrons first? The one that has the highest value for electronegativity, in this case fluorine, will grab it first. But now, let's say fluorine is not part of the campfire. All the rest of the elements are. Then, who will grab it? Yes, oxygen, because it's second boss, right? Second highest electronegativity value. So what if F and O are not there? Then the next one will go in and grab it, which is chlorine, so on and so forth. For oxygen gas, this is how it looks like. The electron density is quite symmetrical, evenly distributed. And for hydrogen fluoride gas, very harmful to us, electron density is unevenly distributed, so we call them polarized, because electron cloud is a bit not balanced, it's slanted towards one side, it's bigger. And this is water molecule, again, is not very symmetrical. So what are inductive and resonance effect? Now for inductive effect, what we have is a group that will push electron or pull electron through the sigma bond. Remember that the sigma bond is the first covalent bond that's formed between two atoms. The first one. For the second and third covalent bond that's being formed, we call them pi bonds. For the inductive effect, what matters is the sigma bond. Now we pull electron through the bond, but doesn't mean I remove it. It's more of like pulling closer to myself. That's all. Okay, I'm still holding to it, but pulling closer. So the effect depends on the electronegative atoms: oxygen, nitrogen, fluorine, chlorine. And this effect dies down rapidly after the first bond. So this is not that strong. It's like only one bond that can do it. Think of tug of war. Okay, so see here, chlorine like to pull electrons from the sigma bond. Oxygen pulls electrons from the sigma bond. Now we have the resonance effect. This means that you have some sort of electron sharing through arrow pushing. So that's what gives rise to resonance structures. You find resonance effect when you see lone pairs of electrons, and we see pi bonds and empty orbitals. Now nitrogen having lone pair is more effective than oxygen because it is less electronegative. Less electronegative means, right, it doesn't want electrons so much. So nitrogen is a bit generous compared to oxygen for electrons because oxygen wants it so bad. So it's a bit stingy towards giving electron. This example illustrates what it means by resonance effect. Nitrogen here uses its lone pair of electrons and push to the adjacent CN bond so that the carbon can feel the electron. And after which, you see that both carbon and nitrogen, they are octet. Very stable, having 8 electrons around themselves. Oxygen can do likewise, but just now I mentioned that oxygen is a pro electron pair donor. Halogens is quite weak because of doing that, it is not that stable. So for the pi electrons, what happens is, right, I can shift this pi bond to the other side. We get the C negative, we get the C positive. Now we use this arrow here because they are resonance structure. These are double head arrow, single line. Okay, it's not the same as the equilibrium one. Let me draw for you again. Resonance, we use this arrow. This is for equilibrium reactions. So they are different. So as mentioned just now, inductive effect, we have pulling or pushing electrons through the sigma bond. This is how it goes using a group as well. So the CO bond, because it's polarized, we have the carbon that's taking a delta positive, delta negative on the oxygen. It pulls electrons in this manner. Same goes for cyano group, delta plus, delta minus, and we have a net positive on the nitrogen in the NO2 group, the nitro group, and this is very, very electron withdrawing. For the resonance effect, we are using arrow pushing from the electrons. So you see for this carbon, we have got one lone pair. We know that because it carries a negative charge, goes in, pushing electrons, form a pi bond, and then this pi bond going to give way because carbon can't accommodate more than 8 electrons around itself. So right now it's got 8. But if we wish to form another pi bond with the adjacent carbon, then you're going to break the existing pi bond with the oxygen. This is still fine because it is still bonded to the oxygen. Now someone asks, which is a better form? The answer is pretty obvious. It is this form here. The reason is because now you compare, the main difference is O carries a negative charge compared to the carbon that carries a negative charge. And because oxygen is more electronegative, it prefers to hold on to more electron density, and that's why this is preferred. Same goes for the second case, this is preferred. Same goes for the third case, that's preferred. This is a good summary for you for this table. The functional groups, family name, and when they're named as substituents, what do you call them? The polarity of the functional group, and of course electronic properties. Do they donate electrons or do they withdraw electrons? And if they do, what kind of effect do they show? Let me introduce to you what are aromatic compounds. As the root word suggests, aroma means smells good, alright? Or rather they smell. Now in organic chemistry, aromatic compounds, they are formally fragrant substances, okay? But right now in the lab, they may not be fragrant to us, but certainly they smell. So they may even be pungent, which is the negative word for being bad smelling. In contemporary chemistry, we use this term aromatic compounds to describe a class of compounds that contain 6-member benzene-like rings with 3 double bonds. Benzene from coal distillate. If you go to Germany or you live there, you study there, and suppose you meet a friend or somebody, say, where can I get benzene? Do not be alarmed because in Germany, benzene means petrol. Just like in America, they say gas, they don't say petrol. This is benzaldehyde. You have a benzene with an aldehyde group, so you join the name benzaldehyde. Preservatives, or you can get it from cherries, peaches, almonds. Toluene is a very oily solvent. This is you can find this in some of the petroleum that we pump into the cars. You can extract it from tolu balsam oil. So aromatic compounds exist naturally in many places. Steroid hormone, the estrone, analgesic morphine, right? See, those in blue, they are all aromatic. And fluoxetine, some drugs here, we call it Prozac. It was a huge blockbuster drug, antidepressant. Many aromatic compounds have acquired non-systematic names that's commonly used for a long time. And because they're used pervasively in the industry, so we give them some nickname. So for a single methyl benzene, we call it toluene. OH with a benzene, phenol. Aniline is like a phenylamine. Acetophenone, show the structure. Benzaldehyde, benzoic acid, orthoxylene. Some markers nowadays they sell it contains this as a solvent. Pretty bad, very flammable. And styrene. Take note, important. Now the carbon 1 will be the one that is the substituent located at on the benzene ring. So how do we name them? This is bromobenzene, nitrobenzene, propylbenzene because of the substituents outside the ring. For arenes are what we call the alkyl substituted benzenes. These molecules got isopropylbenzene, isopropyl of the benzene. This is 1-methylbutylbenzene because remember this is number 1, 2, 3, 4 as a substituent of a benzene. Because right now here in this molecule, benzene is the main functional group. If you use benzene ring as a descriptive word, that means it's an adjective, because it is no longer the highest functional group, then we call it a phenyl group. So phenyl means you have a benzene ring attached to it. This is called 3-phenyl-heptane. Right? The reason is because if the alkyl substituent is of 7 or more carbons, then it becomes the main parent chain. Here we have got 5-a-dimethyl-7-phenyl undec-4-ene. Right? Longest chain is here. Do you see that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? But how do we count? From right hand side, 1, 2, 3, 4. No? Or 1, 2, 3, 4, 5. Of course, from the left hand side, because I want to get the lower number. So it's from here. For di-substituted benzene, we have a common name called ortho. Ortho, not the singer you find in the choir, but ortho means the side by side is 1-2 positions, relative 1-2 relationship. Meta means it's 1-3, and para is a 1-4 relationship. So in this case, we call it a para-substituted chlorobenzaldehyde. For poly-substituted benzenes, we could refer to slide 5, but here let me just run through this quickly with you. This is called 4-bromo-1,2-dimethylbenzene. 2,5-dimethylphenol. Recall that the numbers should be smallest. This is 2,4,6-trinitrotoluene, in short TNT. Remember? You used to sing this. TNT, dynamite, TNT, dynamite. Right? So now you know what this is. You can draw it out. Epiphany. The bond angle in a benzene ring is 120 degrees because it's a perfect hexagon using your math geometry. Bond length 139 nanometers. It is in between a carbon-carbon single bond and carbon-carbon double bond. And the reason is because you have what we call the resonance. You could do a resonance electrons movement here within the ring and see double, single, double, single, double, single. Or you can do it, you can switch, move the gear 1, and you get single, double, single, double, single, double. So you see, when we average these two structure, we get about 1.5 bond on average. So benzene is actually a hybrid of two equivalent resonance form. Neither form will stand on its own, it's always moving. So that's why the true structure of benzene is somewhere between the two resonance form. So that's why some textbooks you see a ring because it's like a hexagon. Then you have got half a bond throughout. So they decide to put a ring. Okay? But no proposal. Benzene is planar. It's all flat because all the carbon are sp2 hybridized with the p orbitals perpendicular to the plane. Here, you see here? Orbital on top, orbital below. Benzene is what we call unexpectedly stable. Unexpected because normally when we find a molecule with a double bond, it's electron rich, so it's prone to attack by electrophile. But in this case, because you have some form of stabilization due to the localization of electrons, we call it aromaticity. So that stabilizes the energy of the system and hence is not so reactive. We can prove this by using enthalpy change of hydrogenation values. And we see that here, benzene, we got this value here, which we expect coming from the test on cyclohexa 1,3-diene and cyclohexene. But in reality, we don't. We get this position. What does that tell you? That means it's much more stable than the diene. And there must be some reason to explain that, right? And we did. So once again, benzene, they are found to cause bone marrow depression. They are not so good as a chemical reagent. That's why you don't really find them in your lab nowadays. Maybe 20 years ago, you find the lab to wash your reagents, to wash your glassware. It's very common. Nowadays, they use something which is very mild called acetone, which some of the girls will use. You find in the nail varnish, turpentine to remove your nail polish. Benzene also leads to Leukopenia, the lower white blood cell count on prolonged exposure. You see that all these aromatic rings. Naphthalene you find in mothball. It is one of the 4 substances that you should know that can sublime. Anthracene, again all these can sublime. Benzopyrene, coronin. You find this derivative in solar cells because they absorb light very readily. So in general, aromaticity can be extended to include the polycyclic aromatic compounds. This is what we mean, poly, many cyclic compounds. Okay, and this is the one of the cancer-causing substance that's found in tobacco smoke. So people, try not to smoke. Not good for your health. Stay healthy. YOLO.